let's see.
I'm sorry, what?
There's a test on Friday, so I understand mostly everything I'm fine with. I just have a couple of questions, this is I think just a review problem.
Okay.
So this says, what are the equations for the vertical and horizontal asymptotes for y equals 5 plus 2x over 3x minus 4?
Okay. Let's do the easiest ones first. Vertical asymptote. What makes a vertical asymptote?
I don't know.
Division by 0. Only division by 0.
Okay.
Okay. So what value of x makes us divide by 0?
With 3, I don't.
Well,
this equation?
yeah. In other words, what you do is take the denominator and set it equal to 0 and solve it.
Oh, okay.
Okay? So x equal 4/3 is the vertical asymptote.
Okay.
Horizontal asymptotes are a little trickier, although in this case, they're not. They're very easy. If the highest degree polynomial in the numerator is the same as the highest degree polynomial in the denominator, then your horizontal asymptote is the ratio of their coefficients. Horizontal asymptote would be y equal 2/3 because the coefficient of x is 2 and the coefficient of that x is 3.
Okay.
So that would put a horizontal asymptote at 2/3. And then the function itself appears to be hyperbolic, meaning it would look something like this.
Okay, yeah.
Now, let's go over the horizontal asymptotes. The vertical asymptotes are easy, just whatever makes the denominator 0. But the horizontal asymptotes can get a little more complicated. First of all, let's consider, we know the situation when the highest degree polynomial is the same. And in fact, if I make this x squared and this x squared, the horizontal asymptote is still 2/3.
Yeah.
Okay? But if I make this x and this x squared, in other words, if I make the highest degree in the denominator, the horizontal asymptote is always y equals 0.
Okay, yeah.
So there's two situations. There's one more. And that is if the highest degree is greater by 1 in the numerator than it is in the denominator, then you don't have a horizontal asymptote, you have an oblique asymptote. Have you had those?
No.
Well, if, in other words, this situation is exactly that. We got x squared in the denominator, x cubed in the numerator. If we divide this into that, we will get a linear function with a remainder.
Yeah.
Well, the linear function is the equation of the oblique asymptote. And usually it looks something like that. And then you might still have a vertical asymptote, and your function might look like this.
Yeah, okay.
Okay? So, and that's really the only three situations. Well, I shouldn't say that. If it's, say, x to the 4th over x squared, well, then you don't have an oblique asymptote. You just have the answer. I don't think they're going to give you any like that. I have not seen that particular type problem ever given. It's always either exactly one greater, producing an oblique asymptote, a linear oblique asymptote. Oblique asymptotes are always linear. They're never curved, I think. At least at this level of math, they're always linear. Up to calculus, at least. So really, that's the only three situations for horizontal asymptotes. Actually, two. It's either 0 or it is the ratio of the coefficients of the highest degree polynomial if they are the same.
Okay.
Want to do another one?
Well, not on graphing. So, yeah, so I've done that one before, so I basically get it. I just needed, like, a
Okay,
refresher.
okay.
And then another just review one for, let's see, an arithmetic sequence. It wants you to find the fourth term of an arithmetic sequence. The fourth term of an arithmetic sequence is negative 64, and the 10th term is 8. And at first, it wants you to find the first term and the common difference of the pieces.
Okay. What's the general equation for the nth term?
A of n equals a sub 1 plus n minus 1.
Yeah, I prefer to put the d. I prefer to put it like that because that's going to turn into a number, and we usually put the coefficient in front rather than d in back. Okay, so what they've given us over here is two equations. In other words, we can say a sub 4 equals a sub 1 plus d times 4 minus 1. And we can also say a sub 10 equals a sub 1 plus d times 10 minus 1. And we know what a sub 4 and a sub 10 is. So the two equations we get are minus 64 equals a sub 1 plus 3d, and 8 equals a sub 1 plus 9d. Now we have two equations and two unknowns. Let's solve those. What's the best way to solve these two equations? Let's call this equation 2. Let's call this equation 1.
So you would set, like, one of them equal, so I guess for the first one, a sub 1 equals 64 minus...
Well, we could do it that way. That would be doing it by substitution.
Yeah.
Personally, I think it's easier to do it by elimination.
Okay.
Let's subtract equation 1 from equation 2. Notice the a sub 1 will disappear and we'll be able to solve for d.
Okay.
What do you get when you subtract 2 minus 1? And I did 2 minus 1 just to make sure we're going to end up with positive numbers, not negative numbers. Negative numbers aren't bad, it's just they tend to make people make mistakes. So if you have a choice of doing something that will result in positive coefficients instead of negative, that's always the way I do it. Notice that if I take 2 minus 1, I get 72 there. I get 0 here, and I get 6d here. Now, d equals 12.
Okay.
Now I can go back into either equation and solve for a sub 1. Well, let's take the smaller one. So I got 8 equals a sub 1 plus 9 times 12. A sub 1 must equal minus 100. So your first, I'm sorry, what?
Okay. Oh, sorry.
So the first term would be minus 100. The common difference, what did we figure it was? 12. So the next term is minus 88. The third term is minus 76. The fourth term is minus 64, just exactly what we expected. That's just a check. In other words, this last step isn't really necessary, but it does make you feel more comfortable about your answer.
Okay. And then, let's see.
And that's always the way you need to do that problem. You don't necessarily need to solve it by elimination. You can solve it by substitution the way you were doing. You'd have gotten the same answer. But when they give you the fourth term and the 10th term, the only way to get a sub 1 and d is to come up with two equations and two unknowns.
Okay. And then, let's see, the next part, it just wants you to find the sum of the first 50 terms.
Okay? What's the equation for the sum of the first 50 terms? N divided by 2 times a sub 1 plus a sub n. So what do we need to figure out?
Let's see, what the 50th term is first?
Yes. So we know our equation is that, and we know the 50th term would be a sub 1. What did we figure a sub 1 was? Minus 100?
Yeah.
Plus the common difference of 12 times 49, n minus 1. What does that equal to?
Let's see. That is 12 times 49.
49. 12 times 49.
Oh.
In other words, the 50th term, n minus 1 has to be 49. What was the number?
488.
Did you already subtract the 100?
Yeah.
Okay. So we know that a sub 50 is 488. So now we can plug in everything.
So then you do 488 equals 50 divided by 2.
No. 50 divided by 2 because n is 50. First term is minus 100. The 50th term was, what was it, 488?
Yeah.
There's the sum of your terms. 25 times 388.
25 times 388. 9,700.
Uh-huh.
Okay.
And if you ever forget this definition, use a small sequence to figure it out. In other words, I know what the sum of the first four terms of an arithmetic sequence 1, 2, 3, 4 is. That's 10. Okay? So, this better, if I've remembered it correct, then 10 has to equal 4 divided by 2 times 1 plus 4. And it does. So I got the sum formula correct.
Yeah.
And that's a good thing to use with math in general. Is if you have a complicated formula to memorize, and you're not positive you got it right, well, apply it to a very small arithmetic sequence that you can do by hand. In other words, I couldn't do the other one by hand. I couldn't list out 50 terms and add them up. So I don't know that that answer is right or not. But at least I used the correct formula, and I don't have any doubts about it now because I tested my formula on a sequence that I knew what it was.
Yeah. Okay.
In other words, I didn't get the n. The first time I think we worked, I had 2 over n, which was backwards. And that's because I didn't test it on a known sequence.
Okay. Alright, and then I just have one more type of problem, which is finding roots
Okay?
in like a polynomial.
Uh-huh.
So let's see. In this one, it just wants you to find. Oh, wait, and then a really good question. When it says find the rational roots, rational zeros, is that the same thing as finding the roots?
Not quite. The roots don't have to be rational. You could have a root square root of 2.
Oh, okay.
But what the rational factor theorem says is if there is a rational root, in other words, a whole number or a fraction or a rational number, then its numerator will be a factor of the constant and its denominator will be a factor of the coefficient of the highest degree term.
Okay.
Okay? So, if we had, you have a polynomial for me?
Yeah. So for this one, let's see. Where to go? Okay. So this one, it's f of x equals x to the 5th minus x to the 4th minus 7x to the 3rd plus 11x squared minus 8x plus 12.
Notice that all the terms in the middle don't have anything to do with the rational factor. The only 2 terms that control the rational factor are that one and that one.
Okay. So what happens? So then it was like 3x to the 5th. How would that change it?
Well, first of all, in this situation here, our numerator has to be factors of 12. And it's plus and minus because minus 1 times minus 12 is equal to 12.
Yeah.
So those are our possible numerators. Our possible denominators are factors of the coefficient of the x to the 5th term, which is plus or minus 1. So basically that means that those are our potential rational factors. If we wanted to test them, and that's all you can do at this point, we would synthetically divide 1 into the coefficients. And if 1 is a solution, I will get a 0 right here. That's the zero factor theorem.
Okay.
In other words, if something is a 0 of a polynomial and you divide it into the polynomial, you have to get a remainder of 0. If you get a remainder of some number, then it's not a factor, meaning it's not a 0. And I don't know which of these might be zeros, and the only thing I can do is test every one of them. So these problems become extremely long. You're never going to have more than one of these on a test, because this could be a 20-minute problem all by itself. I mean, look at how many we have 6 times 2. We have 12 possible answers, and very little to determine which one it is, other than synthetic substitution, which is very useful because we can do it quickly. Let's see if 1 is a solution. You know how to do synthetic division?
Yeah.
Okay, I'll do it real quick. That is not a solution, because it didn't produce a 0. So
So then, what is, okay.
So I go back, and I try minus 1. And I cross off the plus 1. Actually, I guess I cross off the minus 1, because the first time I did it, no, I'll call these the solutions. So plus 1 is not a solution. I'm going to try minus 1. If that's a solution, I'll get a 0 here. Furthermore, the string of numbers that shows up down there is my second factor. It'll be x to the 4th something. In other words, we're not only synthetically substituting to see if minus 1 is a solution, we're actually synthetically dividing, and if it is a solution, it'll produce a 0 along with the other factor. And then we repeat the whole thing over again. In other words, we whittle this down by trial and error until we find a solution. We divide it. That produces a quartic polynomial, which we then have to check all over again. If we find a solution to that, we divide it. That produces a cubic. Eventually you get down to a quadratic. And the moment you get down to where you have a bunch of linear factors and a quadratic, well then you're done, because you can always apply the quadratic formula to the quadratic. To end up with 5 linear factors. Okay? So these are brutes. When you have to use the rational factor theorem and the zero remainder theorem to find the roots of a polynomial by hand, it's really hard. And this was with a coefficient of 1. Imagine if we'd had a coefficient of 12 there. Then we would have had all these as possible denominators also. And then I would have had to take all possible combinations, including 1/12, 4/6, all of those. So that's the way you do it with the rational factor theorem. I'm happy to answer any more questions you have on it, other than the fact that we don't have time to do another one.
Yeah, let's see.
You can't do those in 3 minutes.
Alright, well I don't have, I think those are all my questions.
Okay. In the 3 minutes, I can tell you one thing.
Okay.
When you have a polynomial, if you have complex solutions, let's say that they give you a quartic, and they say 2 minus 3i is one solution. What are the other 3? Well, first of all, complex solutions always come in pairs. They never come isolated like this. So if this is one solution, the other one is this, automatically. Well, if I started with a quartic, well, after I divide it by that, I'll be down to a cubic. After I divide it by that, I'll be down to a quadratic. So now it's really just a quadratic problem. And I can synthetically divide by these complex numbers. Same way I would a real number. Same exact way.
Okay.
The other thing that comes in pairs are irrational solutions. If I come up with a solution like that, then I know for sure that that is also a solution. These are irrational. But that's one of the ways they like to give problems, is they'll give you a quartic, and they'll give you one imaginary or one irrational solution and say, take it from there. Well, you know that 2 plus square root of 2, and then divide by each of these, and you'll be down to a quadratic, and use the quadratic formula if you need to.
Yeah.
From there. Okay? All right. Sarah, I hope that's helpful, and I will talk to you next time.
Great. Thank you.
Bye-bye.
price